Okay, let's get started. So we're going to start discussing essentially the foundations of this class this week and next week, where we'll derive the equations of universal mass. So in order to do this, we'll first need to move from a Newtonian conception of gravity to a more modern conception of gravity. So in Newton's theory, gravity is a force. Any two masses interact with each other, and there's actually a distance, and any two masses in the universe attract each other according to the inverse square of their distance, proportional to each of their masses. So in Einstein's conception of gravity, that's not how it works at all. The presence of mass or energy, so the two are equivalent concepts because of the famous relation E equals mc squared, the presence of mass or energy distorts the structure of space-time, and in consequence, objects in space-time move according to the curvature of the geometry. So there's a relationship that's the mass curves space-time, and consequently, the curvature of space-time tells the mass how to move. So we'll discuss how this comes about today. Okay? So I've been told that I should slow down, so I will try to do that. But if I'm going too fast, you should stop me and tell me to go slower. Okay? Okay, so we discussed there are certain forces in nature. The forces tell particles how to interact. So the first force being ever discovered was gravity, things fall. And then there was electromagnetism. And then there are two more subtle forces, the weak force and the strong force. Strong force explains how protons and neutrons are bound together, and the weak force explains radioactive decay. So those are the forces that we encounter. In addition, if you like, there's a Higgs force, which endows objects with mass. So weak force is operative on length scales that are like 10 to the minus 18 meters. The strong force is operative on length scales that are like 10 to the minus 15 meters. So these are short-range forces. They're only effective over very short distances. Whereas electromagnetism and gravity, these are long-range forces. So the approximation we're using is an approximation in which the universe is homogeneous isotropic. So that's operative on scales of roughly 10 to the 2 megaparsecs. So these long-range forces are the ones that are relevant at this distance scale, at 100 megaparsecs. Now, we know from our refrigerator magnets, electromagnetism is a much stronger force than gravity. So we know, for example, the repulsion of a pair of protons which both have a plus charge, is about 10 to the 36 times more powerful than the gravitational attraction. But it turns out that the universe is electrically neutral. On large scales. As a result, the force that's really describing what's happening in the universe is gravity rather than electromagnetism. Even though electromagnetism is a long-range force, it's many times more powerful than gravitation. Okay? So, Newton, around about 1687, in his Principia, presented the idea that gravity causes masses retract. And this idea of universal gravitation that Newton espoused explained that the fall of an object on Earth because of gravity is the same force that sustains the motion of the planets. So there's a universal force of gravity, and this universal force has a behavior that's attractive, so minus g Newton, m1, m2 over r squared in the radial direction. So one observation to immediately make is that the force of acceleration is independent of the mass. So the acceleration is minus g Newton m1 over r squared, and this is independent of our mass m2. So this explains why heavy objects, the lighter objects, experience the same force of gravity when you drop them. So this idea insists that, okay, so we discussed previously that there were these axes. One axis was g Newton, one axis was speed of light, and here we had Galilean mechanics. Here we had special relativity. Here we had Newtonian mechanics. And over here we had general relativity, where you had both gravity turned on and the speed of light being finite. So we noticed that general relativity reduces to Newtonian mechanics in the limit where gravity is weak, and in the limit where the speed of light is negligible. So we see that it's not that Newton was wrong, it's that Newton's theory is a limit of general relativity. Okay? So ideas in physics which are successful and that they're predictive and you can use them to test theories, they're never wrong. You just have limited regimes of validity sometimes, and they're subsumed by some other theory, which is valid over a larger regime of validity. So in general relativity, there's a famous equation. G mu nu is r mu nu minus 1/2 g mu nu r, which is equal to 8 pi g Newton to the 2 to the 4th 2 meters. So this is a tensor equation. The details really don't matter. The important thing is that this side is geometric, and this side concerns the behavior of matter. So geometry responds to the presence of matter, and conversely, matter responds to the curvature of spacetime. So that's the basic idea of general relativity. So GR recovers Newton in the appropriate limit. So one of the somewhat apocryphal stories is that Einstein conceived general relativity with a thought experiment. The thought experiment would be, suppose the sun suddenly disappeared. What would happen in the Earth's orbit? So light takes 8 minutes and 20 seconds roughly to travel from the sun to the Earth. So if there was a universal speed limit, as special relativity insists there is, then the Earth shouldn't know that the sun vanished and respond gravitationally in response to the vanishing sun for 8 1/3 minutes. So this was the thought experiment that Einstein had in his mind when he described general relativity, because his Newtonian force law is action at a distance. Every mass is instantaneously aware of its distance to every other mass, and the force of gravity is a response to that separation. Okay? So we're going to see how general relativity develops. So the equivalence principle is the key idea here. So we'll argue that the equivalence principle, which equates the presence of gravitational field to acceleration, is the driving idea. So in the absence of so Newton's second law, it says in the absence of forces, an object which is in motion remains in motion at a constant velocity. So the change in the object's velocity, the acceleration, is describing what the force is doing. Okay. So the proportionality constant is inertial mass. It's the resistance of an object to a change in its constant velocity motion. So there's another concept, mg, which is gravitational mass. Which is the response of an object to a gravitational field. In principle, these are different concepts. One is a resistance to a change in the object's velocity. One is a response to an external gravitational field. Okay? There's no reason why these two should be the same. But if you measure the inertial mass of an object and the gravitational mass of an object, it turns out the two are the same. So this is one version of the so-called equivalence principle. So, if you look at the acceleration of an object due to gravity, this acceleration is minus g Newton, some other mass, r squared. We put the subscript g, indicate this is a gravitational mass rather than an inertial mass. And then the ratio of mg to mi. Okay? So mg to mi, this ratio, is 1 plus the correction maybe, which is smaller than 10 to the minus 12. Okay? So this is the description of how an object experiences gravitational acceleration. So the acceleration on Earth is roughly 9.8 meters per second squared. And Einstein conceived a thought experiment. So the thought experiment posits that you're in an elevator and you can't see outside. And yes?
What's that? The 1 plus, there's a seat, isn't that what?
Which one?
The mg by mi is supposed to 1 plus something.
It's 1 plus a correction that's no bigger than 10 to the minus 12. Okay, so let's consider two cases. One is that the elevator is static, where it's moving with constant velocity. And you're inside, and you fall down due to gravity. So you experience gravity inside. U are static. Or moving at constant velocity. And the elevator is accelerated upwards. So here, the acceleration due to gravity is 9.8 meters per second squared. We'll accelerate up at the same rate, 9.8 meters per second squared. So the question is, can you conceive of an experiment to distinguish between these two possibilities? Suppose this is your laboratory. You'll have to do any experiment you like in the laboratory, except for looking out the window, because there is no window. And you need to distinguish whether you're in a gravitational field or whether you're accelerating with a constant acceleration. Can you come up with an experiment that can distinguish between the two cases? Yeah.
Isn't there a small differential in gravitational force on the top and the bottom of the elevator? So your head is slightly less attracted downwards than your feet are.
That's possible, but it's a second order effect here. Well, Einstein couldn't come up with a difference between these two cases. So these two labs are the same. And because these two labs are the same, Einstein is able to explain why mg equals mr. You're experiencing the same effect with acceleration as you are with a gravitational field. Okay? So this idea of the equivalence principle, the equivalence of acceleration and gravitation, and explains the equivalence of gravitational mass with inertial mass. But it's a principle. It's not something which you can derive. This is an idea that's inputted into the theory at some level, in that this is your starting point in developing your theory of gravity. You can't distinguish between acceleration and the gravitational field. So what about light? There's a famous principle in optics called Fermat's principle. He's the guy with the theorem. His observation was that light travels between 2 points in order to extremize the travel time. Usually, extremization means you're minimizing something. There are setups, however, in optics where you're maximizing something. So that's why I use the word extremize instead of minimize. Okay. So whatever light's doing, in whatever setting you find it, light's traveling between any 2 points that you choose in such a way that you're at an extremum. Okay? So the first derivative is something vanishes. So what happens when we shine light in the elevator? So suppose we look at the case where the elevator is attached to a rocket and it's accelerated. So you shine light from here to the opposite wall. Because of the acceleration, light will bend. Similarly, because of the principle of equivalence, the gravitational field, light will also bend. Okay? So Light does not travel on straight lines. Light travels on geodesics, which in this case minimize the distance between 2 points. Okay, so special relativity tells us that the speed of light in vacuum is constant. So light travels along geodesics, which extremize the distance, and in flat space, if you extremize the distance, with a straight line. So, because we're not traveling on a straight line here, what this means is space is curved. We're not in flat space. So here, not a straight line, implies not in flat space. So space is curved. It's non-Euclidean. Okay, so one can show all of these things very precisely, but since it's not a class in general relativity, we're not going to do that. We'll just be a bit more qualitative in our discussion of general relativity rather than deriving all these things. Okay, so special relativity puts space and time on equal footing. And it also puts energy and mass on equal footing. So instead of thinking about space and time separately, we think about space-time. And similarly, just as space and time are on equal footing, energy and momentum are on an equal footing. You think about energy and momentum rather than these two as separate concepts. So, there's a theorem. This is one of the more famous theorems in physics. It's called Noether's theorem. Curiously enough, Noether's theorem was developed in 1915, the same year as general relativity was developed. Noether's theorem says that conservation laws in physics are related to symmetries. So, the conservation of energy, for example, is related to time translational invariance of your system. If you look at the system at one time, system at a later time, this quantity of energy is the same in the system, because the system is invariant when you change it in time. Similarly, conservation of momentum related to space translations. So the momentum is conserved separately in the x direction, the y direction, and the z direction, because the momentum is conserved as a vector. That corresponds to translational invariance in the x direction, the y direction, and the z direction for your system. So, what symmetries inform general relativity? We'll see as we proceed. But in effect, what turns out to happen is a gravitational force is fictitious. So what I mean by fictitious is that a falling body follows a geodesic in space-time. So the presence of the curvature of geometry is what determines how you fall. So the difference between Newton and Einstein, aside from their living centuries apart, is that they conceive gravity differently. So Newton was working in a context where there's an absolute space and an absolute time. And within this context, Newton tells us that mass tells gravity how to exert force. And this happens instantaneously. And the force tells an object how to move. Whereas in Einstein, energy and momentum tell space-time how to curve. And curvature tells matter how to move. It moves along geodesics. So because gravity only propagates at the speed of light, Einstein was able to resolve this tension in his Gedanken experiment. So if the sun suddenly disappeared, the Earth would continue moving in its orbit for 8 minutes and 20 seconds before it flies off tangent to the orbit. Okay? So that's just a short summary of what general relativity says. We'll apply these ideas in the context of cosmology as we proceed. So the assumption is that the homogeneity and isotropy inputs are applicable. So in this context, the equations we'll derive are only applicable on scales of 100 megaparsecs and bigger. Any questions? Okay, so I want to change subject briefly and talk about geometry. In particular, I want to discuss non-Euclidean geometries. So geometry as a discipline was formalized by Wits, and there's a famous book by Euclid called The Elements. And essentially, every mathematician learned out of the elements for several thousand years. So the elements systematize the idea that you start off with certain axioms, and based on these axioms, you derive results through a process called proving theorems. The axioms are things like there exists a point. The point is zero-dimensional. The line, which is one-dimensional, etc. So those are the axiomatic structure you start out with, and based on these axioms, be able to obtain results. So in addition to these axioms, Euclid had a bunch of postulates. There are 5. First postulate is that a straight line can be drawn between any 2 points. So, straight line segment. The second postulate is that a straight line segment can be extended to an infinite straight line. The third postulate is that given any straight line segment, we can turn it into the radius of a circle. So one point is the center of the circle, the other point, if you just rotate the circle in the plane, describes the locus of points that are equidistant from a single individual point. Okay, so that's the third axiom, third postulate. The fourth postulate is that all right angles are congruent. And the fifth postulate is there is at most one line that can be drawn parallel to a given line through a point not on the line. Okay, so that's the starting point of Euclidean geometry, plane geometry, and starting from the axioms and these postulates, you can prove a bunch of things, like, for example, the Pythagorean theorem. For a long time, people thought this fifth postulate was unsatisfactory. People thought this fifth postulate should be a theorem in Euclidean geometry that you can prove based on these other postulates and also the axioms you start out with. Okay? So, for a long time, people tried to prove this fifth postulate. No one succeeded. The story was essentially from Euclid's day until the early 19th century, pretty much unchanged. But around about 1813, Gauss, he described non-Euclidean geometries, which are perfectly sensible geometries where this fifth postulate is refuted. You can refute the fifth postulate in 2 different ways. It could be that through, so you give it a line, give it a point not on the line, you can imagine that through this point, there are no lines which are parallel. Or you can imagine that there are infinite lines through this point that are parallel to this given line. Those are two different ways of refuting this fifth postulate. So, Bolyai and Lobachevsky, independently, this is around 1830, they looked at what's called hyperbolic geometry. In hyperbolic geometry, there are an infinite number of lines through this point parallel to this given line. In 1854, Riemann looked at elliptical geometry. In which every line through this point intersects this line. So elliptical geometry you can think of as, for example, the geometry on the globe. You take any 2 points, the shortest distance between these 2 points lies on a great circle. Every great circle intersects every other great circle. Okay? So this great circle here will intersect, for example, the great circle described by a circle through the poles, or the equator. So here, lines always intersect. In the hyperbolic case, the point P, point L, there's lots of lines to this point that never intersect this given line. So an example of hyperbolic geometry is called the Poincare disk. So if you've seen Escher prints, so these Escher prints are tessellations of say, the plane with figures like fish. The points where the fish heads meet in these Escher drawings, those points are equidistant in this Poincare disk. Okay? So that's a picture of what the Poincare disk looks like. And a way to characterize when what kind of geometry you're looking at is using what's called a Lambert quadrilateral. Suppose you've got a quadrilateral, so a 4-sided figure with 3 right angles. Okay? So if this fourth angle, theta, is less than pi over 2, you're hyperbolic. If theta equals pi over 2, you're Euclidean. And if theta is bigger than pi over 2, you are elliptical. So what this tells you is that rectangles only exist in Euclidean geometry. So if you take 4 points in the cosmos, and you have all these legs longer than 100 megaparsecs, then by measuring angles, you can determine what kind of geometry you live in. Whether it's elliptical, whether it's hyperbolic, or whether it's flat. The problem is we can't do this experiment. So we need to infer various things on the geometry of space-time without being able to measure angles. Okay, so I want to discuss curvature. So is everyone happy with this? Any questions? So we need to choose some notation, and the problem with notation sometimes is that everyone chooses notation differently. So I'm going to call positive curvature a sphere. So let a sphere be positively curved, and I'll let a saddle be negatively curved. So if I have a sphere, and I've got a triangle on the sphere, I have angles gamma, beta, alpha. The sum of the angles alpha plus beta plus gamma will equal pi plus alpha. Okay. So if you think, for example, maybe you can draw this better. That sphere. Then we draw two lines from the North Pole to the equator. These angles are always going to be 90 degrees. This angle can be anything I like. So in particular, I can think about, so this angle alpha. So the sum of the angles is bigger than pi. If I were to draw a saddle here, if you've got three angles here, alpha, beta, and gamma on a saddle, the sum of these angles is less than pi. And this is positively curved. This is negative. Okay, so next time we'll start studying some aspects of non-Euclidean geometry in a bit more detail. Any questions? So tutorial 1 is due tomorrow. We'll go over tutorial 2 with tutors if necessary, and I posted the third tutorial to the website along with the notes. I'll put the lectures on YouTube when I get a chance to take care of that. Right, see you next time.